Good morning, everyone. Welcome to the IPCOS webinar. This is the fourth webinar we have done this year. All have been focused on controls, either basic or APC, for various process industries. Today's focus is obviously on PID tuning, and there will be some tips and tricks regarding that. I would like to introduce you to our presenter today, Gustavo. He has an extensive experience over 13 plus years in doing projects in the areas of process control and optimization. Majority of the projects are helping the clients in achieving their improvements in their stability of the plant or improvements in getting their higher throughput, etc. Take it away, Gustavo. It's yours.
Thank you, Javi, for the nice introduction. Thank you all for attending this webinar today. So I'm going to present, as the title says, some tips and tricks for PID tuning, right? I'll start with some background on the PID controller, mainly the feedback action. Then I'll give you an overview to introduce some steps to tune a PID loop. Right, we are going to see some tuning rules. I'll show a comparison between the different rules we normally find when we are trying to tune a loop. And then on the second part here, we are going to talk about real systems and real problems that we face when we are trying to tune a PID loop. Right, I'm going to show some good practices and share my own experience when talking about real systems, right? And in the end, I want to present a power tuning software that can help us when we are facing these issues in real systems. Okay, so first of all, what is the PID controller, right? So it works basically using this feedback mechanism, right? And the control output of the controller will be a combined function of these three gains, right? Proportional, integral, and derivative. Normally they are based, or by default, they are based on the error, being the error the difference between the set point and the process value. Okay, and here this picture is a pneumatic controller, when in the past we could tune a PID loop by switching these knobs to the right or to the left. I've never tuned one of these, but I saw some in operation, which was pretty good back at that time. Okay, PID loop is widely used in industry, right? So we have only these three parameters to tune, but even so, it's not very easy to tune them, right? And one, it's mainly used because it's very robust and yeah, easy to keep it working. Okay, if we look behind that controller, what we see here is the combination of these three actions, right? Proportional, integral, and derivative. And they are combined to sum, let's say, so to calculate the output of the controller. The output will be written to the process. It can be a valve or the pump, the speed of the pump, for example. And these will make a change on the process, which will be updating the error every cycle that the PID runs, right? So this is basically the feedback mechanism. What we have here is the parallel algorithm, right? So we see that the parameters, they don't interact with each other, right? But depending on the vendor, we can have different configurations here for these gains, okay? And when we talk about PID controller, there's a clear association between the responses of each term here on the controller response. Let's say we can see here a set point change on the closed loop, and this first kick here will be given by the proportional action, right? Which will be based on the current error or the difference between set point and PV. Then we have the integral action will be which will sum all this error here between or below the set point to the PV, right? And this action here will eliminate the offset. And we also have the derivative action, which will be based on the steepness of this slope, let's say. And this action will help to smoothen the response of the PID loop or the PID controller. Okay, and if we represent that in block diagrams, and here C is the controller and G is the process as the Laplace representation of these two. If we write the sensitivity function from the set point here, RT to the PV, right? This is the direct path divided by the feedback. If we rearrange the terms here, we can see that the controller C will be the inverse of the plant, 1 divided by G, multiplied by what we can call a performance function, right? So, and this is important for us to understand that the controller is based on the plant. So we cannot just guess these parameters here, but they are related to the plant. And that's why we need a model of the plant to find in the end a good tuning for our loop. Okay. So PID tuning, how do we tune a loop once we know all these details? So first we need to find the process model, right? So we need to fit a model to our data. Here I'm using a first order plus that time model, right? So in the end, if we want to find the process model, we want to find this Kp constant, time constant, and that time, right? Once we have this model, we can compute the tuning parameters. We can choose tuning rule that we like or that we want to use, and compute these parameters here, gain, tau E, and tau D for the controller, right? And after that, we can adjust the loop response or adjust the parameters manually. So until we have a response that we are happy with. Okay. So in more details now, the steps to find this process model. Okay. This is very straightforward. So what we need to do is put the loop in manual mode, right? Then we step the output of the loop, wait until the process becomes stable, right? And then we find these parameters that will give us the model of the plant. Here on this picture here, what we see, this is the change on the step on the output, right? Then we have this dead time from the time we did the step until the PV starts to move. Okay. Then from that time until the PV reaches 63% of the final value, that will be the time constant. And the gain, proportional gain, will be the total change on the PV by the total change on the valve position, right? Both divided by the ranges. So this is not difficult, right? I mean, it's once you have this data or you have the open loop data, you can try to fit the model so you have the process model for your PID loop. Okay. And in the end, we are finding these 3 parameters for the model. So once we have the model, we can select a tuning method, a tuning rule, and then compute the tuning parameters based for the rule that we want to use. Okay, here we have a table with different methods, and it's clear to see that for all methods, the gain will be always the inverse of the plant gain, right? We see here different parameters, but they are always using the inverse of the plant, multiplied here by desired closed loop response, let's say. Okay, this is for the gain, and tau E and tau D will be normally function of the constant time constant and dead time of the process. Okay, so these different methods, they have different robustness or performance that they can achieve, right? And that so you can use a different method for each loop that you want to tune. Okay, but then how do we know which one to use, or how do we know if these numbers are too big or too aggressive or too slow? It's difficult to have a notion of that, right? So what we can do here is to compare these different methods, right? And we see on this graph here, the gain as a function of the dead time, right? So for all methods, what we see, or for all rules, is that the gain is inversely proportional to the relative dead time of the process. But even so, we can see that's very, we can find different gains, right? For example, for a very small dead time here, the gain that we use in the controller can be 6 to 12 times the process gain, which is a lot, right? And we see the same here when we have relative dead time of 0.5, let's say. So the dead time is half the size of the time constant. And we can see that we can find gains from 1 to 3.5 or almost 4. So yeah, the response will be very different if we choose this method here, B, for example, yeah, CHR, or if we are using D here, which is going con. Okay. And we have the same analysis for the other parameters. Yeah, this is for the integral time, and we can see that some remain constant. So they are constant even so the dead time is changing, right? But almost all are proportional to the dead time. And the same for the action. So this is for you to see that when we see just a table like this, it's difficult to have a better or the best understanding of how these parameters change with the process model, right? And we can see that the responses can be, or at least the gain or the integral time that we calculate, they can change a lot depending on the rule that we are using, right? That's the message here. So these rules that we just saw, they are for a self-regulating process, right? And here I have one rule that I like to use for level, which is the averaging level strategy, right? This was proposed by Zach Friedman here in a paper in 1994, right? And the idea here is to not to use a very aggressive control, but to use the volume available inside columns and tanks to absorb disturbances. So the idea is if you have a level controller with a conventional tuning, what will happen is that if you see, or if disturbances affect the column, right, the controller will try to keep the PV on the set point, and it will try to achieve that by changing a lot the valve position or the slave control here, if you have a flow controller, for example. And that, in the end, will transmit or even amplify the disturbances to the downstream system, right? And the idea of this averaging level is to allow the level to change or to move inside the equipment here, right? To try to absorb as much as possible of the disturbance in the inlet, right? Which will be beneficial for the downstream processes. And how we do that? So this method here, we need to define some parameters. which can be defined based on historical data. Let's, for example, maximum input disturbances, the accepted variation you want for your level, which will be different, for example, from the alarm limit to the set point. And we can use 10 to 20% here. And we also need to calculate the surge volume to be occupied by this disturbance, which is this one here. So in the end, you don't need to step test the level, the controller, but even though you can find good parameters for the gain and for the tau e. Okay, and the idea here is to have a smooth response on the level controller. Good. We could also use this method for a reflex drum, for example, but then we could we need to select a variation that is smaller, for example, 3 to 5%, something like that. Okay, and so we know the process. We have computed the tuning parameters, but in the end, what we need to do, we always need to do some manual adjustments, right? So we need to change the gain or the integral time or derivative time, so we can have a response that is more or less the response that we want for that loop. For example, here, if we want to reduce oscillations, for example, what we can do is to reduce the gain, right? So the drawback here is we are going to make the loop slower, right? We can also increase integral time. Remember here that the integral time is normally 1 divided by integral time. So if we are increasing the number here, we are decreasing the integral action, right? So as we do that, we are also reducing the oscillations in the loop. And we can also do that by using a D time or increasing the D time to help to eliminate or reduce the oscillations in the loop. Okay, so this is the steps that we do. So normally you find a model, then you choose rule that you want to use, and in the end you do some manual adjustments to until you find or until you are happy with the response of the loop. Okay, so but which rule should I use? We saw that there are many available you can find on internet, and yeah, that depends, right? So that depends on the performance criteria, the loop that you are tuning, the limitations you have, right? So you don't want to use a very aggressive rule or a rule that gives you very aggressive response for a loop that you want to be stable, for example. So as suggestions here, what I like to use, or I liked to use in the past, was using IMC for self-regulating loops, right? Because here we have a response that is more robust or slower, in other terms, than the other rules, right? And is suitable for relative large dead times. And we have this tuning parameter. We have this lambda, which is the closed response you want for the loop. So it's easy to change the response by changing this lambda parameter. Okay. And for level controllers, I like to use this Zach-Friedman strategy, where we set a smooth response and there's no need for step testing. And we have also this tuning parameter, which is the allowed error on the PV, right? And which structure should we use? Normally, we use proportional and integral action, right? That should be appropriate for most of the loops. If we see here in the table, we only need, or normally we use the action for temperature controllers, and if you have a composition controller, for example, that is slow and with dynamic, more complicated dynamics, then we should use a D action. And if we want to use a D action, then it's better to use the D action on the PV, not on the error, because then we don't have any problems if we need to change the set point of the loop, for example. And again, if we are using D action, then we should use a proper time lag for this.
Hey, Gustavo, can I break you for a second? Could you please close the Bruno, your chat message?
Say it again.
There's a chat.
Oh, this one?
From somebody from Bruno is popping up on your screen.
No.
It's on your screen, Ravi.
All right, sorry.
Okay, should I continue?
Yeah, sorry about that.
Okay. Good. Yeah, so this is when we are doing one single loop, when you are tuning one single loop. Okay, and now that information that I shared is normally what we see when we are finding or we are looking for information on how to tune a loop and so on. But one thing that is not very it's not easy to find is the difficulties that we see for real systems, right? It's a bit more complicated than what we just saw, and now I'm going to show some examples. So if we go back to that block diagram that we saw before, and if we replace this block diagram with real components, right? So the loop now is a DCS. So the loop is inside this DCS. So we don't know exactly what's the equation that is used, what are the limitations, or what else is configured in this DCS, right? The final control element now is a valve, which can have deadband or can be sticky. The model is not only one by one, it's not monovariable anymore, but you have this multivariable effect, right? The loops will interact with each other. It's not, so once we tune one loop, that tuning that we set will affect the other loops that are close to that one. And we also have disturbances, right? So these disturbances can be measured or not, and they will change the operating region for our loops. So it's a bit more complicated than we just saw. So if we just talk about DCS configuration, it's not, so this PID block that is used will be different for each vendor, right? Sometimes it's even difficult to find the equation. You find these block diagrams here, and you need to follow the lines to understand exactly what is configured inside the DCS, right? The equation that is used can be series or parallel or different combinations. So you can have the gain or proportional band, and the units for the time, integral time and derivative time can be also different. You can have, for example, the action on the error or the action on the PV. So what we do here, then we need to convert the parameters that we calculated, right? So we need to convert them to the DCS equation that we have. And how we do that, we need to refer to the DCS manual to find the equation and then manually change or modify or convert the gain and integral time and D time to the DCS that we have, right? And one tip here is to change the existing parameters gradually, right? We don't want to go from 0.1 to 100 in one go, right? So we should do that gradually. And if we talk about the process now, the process not only first order, right? We saw it before that we were trying to fit a first order model in our data. but we know that the process is not only first order, and it's not only monovariable, right? So the responses will depend on the operating point, on the, let's say, the load. If we change the feed, for example, on this column, the dynamics for the controllers will be different, and also the steady state gains, right? And yeah, we also know here that the tuning for the temperature, let's say, will be affected by the tuning on the pressure or on the reflux. So it's not that you can only tune one loop, but we need to consider the effect of the other loops that can interact with the loop you are tuning. So you have this multivariable effect as well. And the idea here is that we need to select the model for a robust control. Okay, so we need to step the process in the whole operating region. If we use, if we use different feeds here, for example, we should test the loop for these two different situations. And the idea is to choose the model with bigger gain and bigger dead time. So that will make, in the end, the controller to respond or to be slower for different conditions, but in the end, it will give us a more robust control. What you can also do if the model changes a lot from one operating point to the other, we could use gain scheduling blocks or yeah, so you can select, or you can have two different tuning for different operating points, for example. Okay. And the tuning, we saw before that, so it's not very easy to define the rule we want to use, because we don't know exactly how these rules were or the objective of each rule. But we know that our loops in the process, they have different objectives, right? And it's not only defining the objective, but you also need to consider the limitations that can affect that loop. You have limitations as disturbances or conditions or inutilities, and you should also take this into account when you're defining the loop for a PID controller. And the idea here, so we need to define the response we want for each loop, right? So that means it's difficult to use the same rule for each of the loops. For example, the temperature, here we want this to be good to set point changes. We don't want to see overshoot. And we know that this temperature controller will be affected by, let's say, this steam pressure here. For the pressure, we want a good reject to low disturbances. We want this to be stable, and we don't want to see oscillations. And we know for this pressure controller that it will be affected by ambient temperature, for example. This ambient temperature can change the cooling water temperature, right? And then we also need to take that into account when we are defining this tuning for the pressure controller. And the same for reflux and levels and so on and so on. Right? So the idea here is that we need to define, or we need to consider each loop individually for setting the desired response we want, but we need to take into account the limitations and impact of the other loops when we are doing this tuning for each of the loops, right? So what we need to do is check historical data to evaluate these loops in different conditions. And we also need to understand the process limitations with operators normally, because they know, or they should know what's happening with the process, and then we can check with them what we need to consider for tuning the loop. Okay. So we see that it's not very, even though the tuning one PID loop might be easy, right? The steps are very straightforward. If we want to tune a real PID, it's a bit more tricky, right? It's not very easy to find a model because that will depend on various disturbances or other loops that may interact. And it's impossible to define a clear specification for each of the loops we are tuning. Right? We might use different methods, but then it can be very complicated. And there are even some details on the DCS that can make it even more challenging. Okay, but the idea is that we need we know that the performance of the PID they degrades with time, right? So we need to make frequent checks, and we could be aware, or one way of doing that is doing frequent checks and being aware of loops in manual, loops with mode changes, loops with set point changes, and changes in the process. So whenever we see one of these, we should we can be sure that there's something going wrong with the PID loop. Okay. Yeah. So it's clear that if we are doing that manually for each loop, that can be very time consuming and costly and even dangerous, right? And that's why we used, or we recommend the use of tuning software. And here we are going to talk about Inca AptiTune. And the idea is this tool is used, or this tool allows you to identify a realistic model, right? So we can use the real model. We don't need to approximate it by a first order or whatever. And the idea is that we can use, or we can balance engineering objectives and performance and robustness specifications, right? So the program will find will fulfill all these requirements and give us the best tuning set for those parameters that we choose. Okay, and the idea is to make it simpler and less costly and also safer. Okay, so when we are using the software, what we need to follow are these steps here. We need to import the step-based data. We need to select the DCS. We identify the model, and we set engineering specifications. And we can see here for these points 2, 3, and 4, these are the ones that we just saw. They're not very easy to do when we are tuning the loops manually, right? So it's here we can select the DCS on the list. We don't need to know exactly the equations or how the parameters are arranged. We can use we can identify a very realistic model using FIR algorithm, right? And we can set the engineering specifications for each of our loops. We can set maximum PV deviation, overshoot, robustness specifications as gain margin or dead time margin, right? And once we do that, we can just click a button and run the optimization, and we can easily find the tuning for those configurations that we are using. And then in the end, we can simulate different conditions and choose the best response that we have or that we want. Okay, and the idea is that on the first time we already find a very good tuning set with Inca AptiTune. And just one thing here, that for this, when we are using model-based methods or tools, what we need to do is to follow a strict workflow, right? And we need to explicitly define the behavior we want for the closed loop. And what is also important is that we need a realistic model, because all the optimization and the tuning will be defined based on that model. And these here are included already in the tool. So once we are using PID Tune, we can easily set these specifications for each loop, and we can have a very realistic model of our process. Okay. I have some nice examples here, real examples where we used PID Tune, and we can compare them with rules or tuning rules to see the differences. So first example is a temperature controller in a heat exchanger. Here they used cooling water in shell and tube heat exchanger, right? And apparently the model is clear here, but it's a tricky one because we have a large relative dead time, right? So we saw on that comparison of the rules that depending on the rule that we use, if we are doing that manually, the gain could change from 1 to 3 something, right? So even though it seems easy to find a good tuning set for this loop here, it's not always the case. And this loop here is also affected by changes in the process. That means the steady state gain and the dynamics or dead time, they can change over time, right? So the gain will change based on the cooling water's temperature, and the dynamics will change based on the operating point. And here we have input-output response. So we are changing the valve position here, and we have the response on the temperature. Okay. And tuning, when we are using PID Tune to tune this loop, so what I did here in this example, I use different data from different points, right? So in the tool, we can select slices or we can remove bad data and do all this model preparation, right? And once we found the model, what I did was to select as engineering specifications a maximum overshoot. I didn't want this temperature loop to be very aggressive here. And I also used robustness specifications because, as we saw, this process was subject to changes in gain and dead time, for example. Then I can select these robustness specifications for in the tool to find the best loop possible, right? And here we see the response, the closed loop response for a step change here. The blue one is the valve, and the red one is the PV, so the simulated response, right? So we have no or very small overshoot here and a good response to low disturbance as well. Okay. And if we want to see for this response different combinations of gains and dead time, right? Because as we saw, it's important for this loop to be not only stable, but also not oscillatory if we are changing these gains and dead time, right? So there's one tool that's interesting there's one feature that is available in the tool where we can check the stability or the open loop and closed loop responses for different combinations of gain ratio and additional dead time, right? So we can just click here on the graph and you see the responses for open loop, for the PV, and for the OP. Okay. And now if we compare the response that we found that we got with PID Tune, if we compare that with other rules, supposing here that we could get the same model, right? Because the model, don't forget that we used aptitude to find that model. But supposing that we could use the same model and apply the other rules here, we can see for aptitude, right? So we have this very stable and robust response. If we use ETI set point here, we see that the response is very aggressive and oscillating, right? Here, if we use SHR, these are some of the rules that we saw on that table, okay? If we use CHR here, it's not very clear, but the output is on this second axis here, right? So for the set point change, the output reached around 40%, which is a lot. So we don't want this to, or we don't want the real process to react like that for a step change. And here the IMC, which is not bad, but it's much slower, or not much, but slower than the one that we have found with aptitude. Okay. So this was the first example. In the second example here, I have a multivariable process or a multivariable model. This was the feed line for a rear reactor, right? So we have one flow controller, which is changing a valve after this pump. And then after that, we have a pressure controller where we are changing the motive here on the ejector. And that is used for pulling the carbamate that is fed to the reactor. Okay, so we can see that we have a flow controller and a pressure controller on the same line, right? And this is multivariable. Okay, so if you see here, if we change the valve position, the model for the flow is like this, and the model with the pressure is like this, right? And the same if we are changing the motive here on the ejector, we have a response on the flow and also a response on the pressure with the different gain here. Okay, and if we are trying to tune this system manually, right? Normally, as you answered during the poll, what we normally do is tune one loop, or the one that's more important, fast, and the other one we are going to detune it, right? But then we need to do some iterations here. We need to find the one loop response that is good, then we need to detune the other one, but then we need to come back to the first one to see if the response is still acceptable or not, right? So we need to do these iterations, and that could easily take a day, or I don't know, a long time to do. And so when we are using aptitude here, what we can do is just set specifications for each loop independently, and then we click a button. And you see the responses here for the flow controller, right? So this is the one that we want more aggressive response. And this is the pressure controller. So yeah, it's very easy, very straightforward to tune both loops at the same time, right? Okay, we also have on the same plot here, we have the responses for the PID controller for the changes on the flow controller, right? And also the response of the flow controller for the changes on the pressure controller. So we can also check how these two loops will react when the other loop is being changed or yeah. Okay. And these multivariable problems, or these multivariable response, they are common to see in different processes, right? You can see that in steam headers where you have flow controllers and pressure controllers. You can see in boilers, you can see even in distillation columns. So it's very easy to find this multivariable problem in real process, okay? And the idea here is that we can do it for each of these systems. We can find all the tuning for all loops at the same time, right? And we do that with fewer iterations, with less costly and safer process, right? And in the end, we find a better control for all our loops and especially the key variables that we want to control. Okay. Yeah. That was it. Javi, do you want to continue with the more information bit?
Yeah. Thank you, Gustavo. That was very good. Please ask your questions in the Q&A while I go through some additional information where you can get more information how to do these things. So next slide, please. We have a special website called www.incatools.com where we provide all of this information available for you. The guide for PID tuning, you can request, you can talk to an expert, any of this stuff. Please go to that website to get a lot of information there. Next slide, please. Yeah, you can download a free demo of IncaTools at the website. For this aptitude software, and if you have trouble in using it, please you can call us and we can schedule a demo on how to use that. Next one, please. Also, there are short videos on how to do these, how to use this software, as well as how to help yourself in tuning some of these tricks. How do you do tuning with no overshoot, for example, how to do tuning of interacting loops. These are all very short 3-4 minute videos, help you, give you some hints how to do that. Yep. One more, please. And again, as I said, there is a demo that you can request for, or you can talk to an expert and also get a limited license that you can download. Last one. And all the theory behind what Gustavo presented can be looked at some of these references that are well published. Yeah, Gustavo, you want to add anything here?
No, yeah, just for the pictures that we saw and the tables and so on, you can find those on these links here.
Yeah. So please ask any questions you have. We have a question and sessions open for everybody. So I have some questions coming through. Let's see. The model from IncaTools can be exported to be used in other simulation software such as Simulink. Now I currently use PIDtuner.com that gives nice continuous first and second order models, but sometimes fails with closed loop data. You want to answer that?
Yeah, you can export a mat file as a FIR model. Yeah, and if you want, you can use in MATLAB, for example, and Simulink. Which is the second bit of the question, Javi?
Sometimes he's using something called PID Tuner right now, and it gives good models, but fails sometimes using closed loop data.
Yeah, closed loop data is tricky, right? Because it's difficult to find realistic models when we are using closed loop data, right? You need the proper algorithm to use or to model this. But even so, you have no guarantee that the inputs are causing the outputs and not the other way around, right? So yeah, it's tricky to use closed loop data when you are trying to find a model.
Yeah. Okay, hope that answered that question. Next question, what are the challenges that you come across during tuning a highly underdamped response? How do you tune it?
Yeah, it depends on the method that or the rule that we are using, right? Yeah, if you are using the software, is not that bad, I would say. But if
Yeah.
not, then yeah, we need to select the proper rule to tune it.
Okay. How do you tune cascade loops?
Cascade loops, we saw you on the pool, that one, right? So normally what we do if we are doing that manually, we need to tune the slave controller first, right? So we do the open loop test on the slave controller, and then we tune the slave controller, and then we step the set point of the slave controller and find the model from the slave to the master controller, right? And then we tune the master controller. So that will be the steps if we are doing that manually. If we are using a software like AptiTune, we can just step the slave controller and then have both controllers tune at the same time.
That's good. What is the best manual tuning methods from all available methods? Is there any? I doubt there is one for any specific process. I think.
I think there's not only one, right? As I talked that I said that I like to use that IMC, but we have some drawbacks when we are using that one, especially for very slow dynamics, because the integral time is based only on the time constant of the process. So if your time constant is very big, in the end you are having a very sluggish response. But at least for that rule, you can select that closed loop response, the lambda, so you can more or less try to cope with these differences between the loops that we are trying to tune. But yeah, it's difficult to say.
Yeah, that's good. How do you tune a system with noise in it?
That's good. Yeah, normally what we can do is we don't want to use a very aggressive tuning, right? Or in one hand, we could filter out the PV, right? But if you need a very fast response, we don't want to do that. So sometimes it's better to ask the maintenance team to have a look or try to reduce the noise on the instrument, right? But definitely we shouldn't use a D-time or derivative action when we have a very noisy system or PV, let's say. So in the end, we should, if we need to or if we cannot remove or reduce the noise, we should use a rule or with a small gain, let's say, because then we are not amplifying the noise behavior.
Yeah.
Okay.
Okay, there are a lot of questions coming through. We may not be able to answer all of them, but we will try to answer what we can. And if not, we will send you emails, responses to these answers. Okay. Do you think there is a best tuning rule in case of large delay or time constant?
Yeah, again, we could have a look on that table or on that comparison between the different methods, but I would stick with IMC. Yeah, but even though if the dead time is too big, then you shouldn't use it. Yeah.
Okay. One of the questions that came is for AptiTune, user system identification and PID PID tuning. what kind of data is required and what are the PID tuning techniques were used in it?
The data that is required is the open loop test data, right? So we need the data from the output and the PV at least, right? And behind the scenes, we use an FIR algorithm to find the model, and then we use an optimization problem, or we solve an optimization problem to find the best tuning using the specifications that were set in the tube.
Yeah. Okay, maybe one last question, because we are already at 11 o'clock here in US. How do you tune an integrating system?
You do the same. You need to step, depending on the rule that you are using. If you're doing that manually, some rules require that you do the open loop step testing, right? But if you are using that Zach Friedman, as I explained before, we can just select or choose some parameters, and based on the vessel or on the information we have from the equipment, we can directly calculate the tuning parameters. Yeah. And if you're using a tool, you also need the open loop step data to be able to tune it properly.
Yeah, so especially when it is integrating, I think it's a lot more easier and time saving to use a tool.
Yeah, and especially because it can be, if you are trying and guessing the tuning parameters, then that can be very dangerous, right?
Yeah, and the tool can tell you if there is integrating and take care of it, right?
Yeah.
So it makes it easier when you use a tool. That's one of the biggest advantages of using a tool rather than doing manually.
Yes, I would say for integrating systems, and as well for these multivariable systems, or once it gets more, if it goes, if it's not like this very simple example that we always think about when we are trying to explain how to do a PID loop tuning, PID tuning, let's say a flow controller. Which normally is not very difficult, but as long as you add like these real characteristics, and you have limitations in your process, and then it becomes more difficult to tune them manually.
Yeah. Thank you very much for asking all these questions and participating today. If you have more questions, please send them to poesales@ipcos.com and go to incartools.com. A lot of these questions are already answered either through short videos or a lot of documentation, white papers that we have there. And if I didn't get your question answered in this 1 hour, we will email your answers to those questions. Thank you again for participating here in this webinar. Have a good day.
Thank you. Bye-bye.